So, my goal for today's lab is that we start looking at magnets, and because magnets are very strange, and because we can't really see magnetic fields, some of the lab is going to be simulator based, but my goal is to be able to physically manipulate some magnetic things with you today. So there is kind of both an in-person element and a simulator element. The in-person stuff, we're going to be working with disk magnets and also electromagnets. Start talking a little bit about the difference between them, how magnetic fields function, and the effect that the magnetic fields can have on electricity. Why?
No.
No? No magnets? They don't make any sense, but they're cool at least.
My desire to understand them outweighs their purpose. And I don't
That's-
understand them.
That's fair.
And I think it's really useful, right? What's that MRI thing? Is that an actual thing?
Yes, I believe the MMRE stands for magnetism, magnetic
You
field.
did an MRI,
Yeah.
magnetic resonance imaging.
That's an important use of magnets here.
Yes, yes it is.
Someone else is strong. It's not mine.
Still, for those of you going into careers in the medical sciences, more knowledge, more better. Right? So this week we will have a lab. It just might be a little bit of an atypical one. Do come to the lab room at the start for the physical parts with the electromagnets, but the second half, maybe second 2/3 of the lab will involve some simulators because I have no way to physically show you the arrows of a magnetic field otherwise, and those parts you can work on independently on your own time if you want, and I'll take the lab up by the end of the week. There's a wellness day this Friday. That doesn't necessarily affect this particular lecture, but because of that fact, I'm probably going to push the homework around because I want everyone to have a vacation this weekend. I certainly need one. Next week is also a normal week for this particular lecture. So we will also have a normal lab next week. The week after that is Tuesday is a wellness day, so no class that day, no lab that week. I'll probably say this every single meeting, every single week until then. Partially to remind myself. But right now though, lab this week, kind of atypical format, stay tuned. Additionally, this week's homework assignment is currently due on this Thursday, that is April 1st, and no, that's not a joke.
Good one.
Thank you. No, I'm aware that most of my ones are terrible. I wasn't waiting on a reply, I was just trying to figure out the next words I'm supposed to be saying. So I apologize for that silence there. My main goal for today is finishing off talking about electrical power, so we can close the book on the chapter 17 notes. But before that, I want to give you a chance to ask about any homework questions that you have already, any issues with the homework that you may have already encountered. But today, after discussing electrical power, that should be every single formula and thing you would need to finish out the assignment by Thursday. It'll be Thursday night, you can ask again on Thursday, and then we'll move further on into magnetic territory.
We had homework due last Thursday too, right?
Yes.
Okay.
And
This homework is a lot easier than last chapter.
I am glad.
Chapter 16 was really hard. This one is not too bad.
That is fair. Circuits make more sense to me. Because resistor circuits I've been working with my whole life. They seem more intuitive at first glance to me. Capacitors are weird.
Yeah.
And
Well, it's
such.
like these questions I knew what they were asking. 16 questions I didn't know.
Again, fair, because the fields and the energy and the voltage within the capacitor itself is harder to visualize than just the circuit working, in my opinion. That is, may influence how we teach the course in the future. So, any questions, comments, concerns, etc., about the 17 homework from what you've worked with it thus far?
I have a question, but it's not directly about the homework.
Okay.
For the resistance, like formulas on the formula sheet, can you just go over which one is which again?
Sure. The circuit resistances,
Yes.
okay. If it's not labeled on there, I apologize.
No, they say resistance, I just don't know which, when you use which one.
Can I take a look at it real quick? Sorry.
I'm sorry, I definitely could help with that situation.
Oh yeah, that isn't labeled at all. Oops, sorry. Thank you.
The middle way.
Okay, for resistance circuits, if they are in series, that's the one where they add up linearly. Parallel is the inverse sum of the inverses. So please do go ahead, feel free to write, label them as such. I'll make sure to revise that one with you. Minor note, when doing parallel resistance, make sure that after you add up the inverses, you then take the inverse of what you just added together, because otherwise your answer is upside down. Okay. So, speaking of resistance, the electrical resistance of any given object, circuit component, machine, etc., has an effect on how much electrical power it draws from a circuit. And electrical power is still power. The same power equals work over time as before, still measured in watts. So when we're talking about the electrical power used up by something in an electrical circuit, that refers to the energy that it draws from the circuit per unit of time. If you have a 60-watt light bulb, every single second it is turned on, it is drawing 60 joules of energy from the electrical current, and if it doesn't get 60 joules every single second, it turns off. So the power being used by something tells you the energy it absorbs from the circuit per second, and any device, machine, light bulb, etc., with a wattage listed on it tells you how much power it needs in order to function. The energy per second it needs to actually do its job. If it doesn't get it, it doesn't work. And part of the bottom here is the most important. This tells us the electrical power something is using based on the properties of it and the circuit that it is in. And this is sort of the original classic formula, power equals current times voltage. If you know the current passing through something and you know the voltage drop across it, you can figure out the electrical power that's currently drawing from the circuit. Separate from that original formula, though, we also have Ohm's law. And because V equals IR and P equals IV, we've taken to combining and recombining these two formulas to get slight variations So P equals V squared over R, P equals I squared times R. It's all the same power formula, just a couple things swapped around and recombined with Ohm's law.
V, voltage, question
Voltage.
mark? Is that it?
Yes, V is voltage.
So this just means that we have options.
We have options, yes. As long as you know two things about the circuit as a whole or the part of the circuit that you're examining, you can figure out how much power it's drawing. And then you can use this to find the third thing. So flexibility is good.
We did this last week.
We did. So this is not entirely new. And you've been dealing with power for as long as you've been doing most science. And at least in American English, when you, prior to like classes where we talk about power as work over time, like when you were in high school or younger, when you heard the word watts, what was the first thing that popped into your head, the first concept?
Light bulb?
Light bulbs, electricity. And that's because, at least in American English, we tend to use the word referring almost exclusively to the wattage of an appliance, how much electrical power it needs to stay turned on. So we're finally actually tying the concept back into the thing that most people are most familiar with it in. It still work over time, though. That has not changed. Now, quick sample. This is the same premise, the same initial part as the resistor that was theoretically built and we found its resistance at 2 temperatures previously. Those 2 resistances for that 20 degrees Celsius and that 3000 Kelvin were 18.2 and about 240 ohms. These should be in your notes. You just don't want to save some time digging them back up and resolving for it. We also figured out how much current would be passing through each of the resistor at each of these temperatures. As something warms up, its resistance increases. As its resistance increases and voltage stays constant, the current will drop. And at each temperature, since we know its resistance and we know its current, we can figure out its power draw at each temperature. So we double check with our power formulas. We know resistance and current. So we know that for those 2 elements, P equals I squared times R. So we take each of our currents, multiply them by each of the resistances, and we can arrive at 2 different power ratings for this particular resistor based on its temperature. Which is another reason why machines overheat, because when they get too hot, they literally can't draw enough power to stay on sometimes. So if you're lucky, it'll turn off, and if you're unlucky, it'll melt. This does not, however, mean it gets more efficient. It might be drawing less power, but it's also accomplishing less. It's not doing the same amount of work for less energy. It's melting. Now, okay, questions so far?
Hours in watts, right?
Hours in watts, correct.
This is just a lowercase w, or
Uppercase. It is inconvenient that the short form for the unit watts is uppercase W, and short form for the variable word is also an uppercase W. We ran out of letters a long time ago, even including the Greek alphabet, because we used rho for like 8 different things. Now, this type of question is on your homework. This is all fine and dandy, but I I know and accept that most of my students never plan on doing anything physics related ever again in their lives. Is that is that a fair assessment? Okay.
Very wise man.
That is valid. I knew what I was getting into when I was assigned this particular class to teach. Even if you never take another physics class or pick up a graphing calculator again, you will still live in a building that runs on electricity. So let's tie this into something you will be doing for the rest of your life, looking at electric bills.
What's that?
So practical skills time. Now, I said a moment ago that every single appliance that you use has some sort of a wattage rating. Let's say that, I got over here, I called this when I wrote it earlier, a 100 watt TV. So when you buy an appliance, you can usually tell somewhere on it, like we have, sorry, rewind. I had to work with my professor here on energy efficiency research as part of my undergrad degree, so I dealt with a lot of this stuff. A lot of appliances sold in the US these days have a yellow tag somewhere on the box, or specifically with the higher draw, higher energy cost appliances, mostly fridges. There's a yellow tag somewhere on them that tells you the energy figures. And most other appliances, it should be somewhere on the packaging. Light bulbs, it's usually written on the top of the bulb itself. And it just mentions what its wattage should be. And that is, again, the power needs to stay on, the energy per second it needs to draw from the current. So let's say you buy a new TV that has a power rating of 100 watts. Me going home, unwinding after work, my TV/desktop computer monitor, same machine, is on for about 5 hours. And this can help us with energy costs, because eventually if you haven't looked at electrical bills yet, you will eventually see that in the US, our grid system charges people a certain dollar amount or cent amount per kilowatt hour of electricity. Now, the unit of kilowatt hour gives me fits from a professional standpoint because it's not a simplified metric unit. It has watts in it. It also has hours in it. It is not actually a unit of power. It is a really weird unit of energy. And we know this because if power is work divided by time, if you take a unit of power and multiply it by a unit of time, you get work, you get energy. And the unit of kilowatt hours is literally 1 kilowatt times 1 hour, so kilowatt hours is technically an energy unit, which means you could convert it back and forth from joules. So you're not billed based on the wattage of the appliance you plug in, you're billed based on how much energy it uses, which depends on its wattage and how long it's turned on. So if this was the only appliance that we're caring about right now, a 100 watt TV that's turned on for 5 hours a night, my red marker. First, we want to find the kilowatt hours used by this particular device. So we convert watts into kilowatts, 0.1, times the number of hours the machine is turned on. And that tells us that every night, this TV uses half a kilowatt hour's worth of energy. So this is energy used, past tense. And this is not a metric approved unit. This is an Imperial American Power Grid unit. It does have a conversion to joules, and I'm telling you this conversion because it might come up on your homework. 1 kilowatt hour is equal to 3.6 times 10 to the 6th joules, which is a lot. I get the feeling that the power system uses kilowatt hours because if they use joules, all the numbers would be way bigger, and that just scares people.
You said that's 3.6 times 10 to the 6.
Correct. So 3.6 million, 3,600,000. Now, this doesn't necessarily factor into the bill. What does factor into the bill is this number and the cost of electricity in your area. I use this term as a sample a lot. This is going to change a lot based on where you live, and also time of day, because peak electrical hours, some companies charge different rate based on the time of day and what season it is. It's a big pain. But, assuming a constant rate, if we use half a kilowatt hour of energy every night, that means it would cost 5 cents to have this TV on every night. So 30 times 0.05 is
$1.50.
thank you. For some reason I forgot how to do all math for a moment there. So, the long and short of this particular ramble is, low wattage appliances like this that are not turned on all the time are not the bulk of your energy bill. Parents might have told you growing up, turn the light off, you're burning electricity. One light bulb left on for 5 extra minutes might cost you a fraction of a penny. The single biggest draws of money in a home are the refrigerator and the air conditioner, because they're big, bulky things that are on all the time. Let me actually, these are figures that I need to have pulled up for this. Let's look up real quick. Wattage of refrigerator. Okay. So, quick sample. Refrigerator. Has an average wattage of 1200, and it's plugged in all day. So, let's just do the same math real quick. 1.2 kilowatts times 24 hours gives about
28.8.
thank you. 28.8 kilowatt hours. So every single day, assuming a constant 10 cents per kilowatt hour that doesn't change based on time of day, the fridge is costing you about $3 every day. So at the end of the month, poof,
93.
yeah.
There's nothing you have to have.
Correct. Now granted, okay, now this math, like the process here is good. Fortunately, the fridge itself, while plugged in 24 hours a day, is not always running at full capacity 24 hours per day. You know, you can usually hear whether or not it is making noise, and sometimes it just isn't making noise. Its coolant pump doesn't always run. It gets your fridge nice and cold, and then when it warms up, it gets it nice and cold again, and the temperature just keeps oscillating within an acceptable degree for food, which means even though it is plugged in 24 hours a day, it's not at full power 24 hours a day. So mercifully, this wasn't an entirely accurate figure, but it is a worst case scenario.
The number's probably closer to like 70, 68.
If it's on 50%, I would say 50% of the time usually it is on or off, based on the research I had to do for my undergrad degree. Yes.
Does a nicer fridge, like a bougie fridge, does it have like a higher or lower like wattage?
That's gonna depend on all the doodads installed in it, the temperature of your house, the temperature you set the fridge to, all the things you keep in the fridge, and how often and how long the door is open. If it's got like the Bluetooth screen on the front that you can take notes and pictures with, that's just gonna take up energy all the time. If you store a bunch of high-density food in there, it takes more energy to get that cold and keep it cold. If you open the door a lot, that's more heat it has to siphon back out, so that's going to cost more. And what was the other point I made? Oh, if your house is warmer, then the fridge has to do more work to keep the heat out of the fridge. Conversely though, if your house is colder, your air conditioner has to do more work to keep the house colder. So 6 to 1 happen.
I got a bougie fridge anyway.
I just don't want a fridge that's connected to the internet. I don't need someone to be able to hack my food or end up controlling my security system through a weak point in my fridge's security software.
Does that happen?
Yes. People have been able to hack into pacemakers because they weren't properly protected.
That is so concerning.
Oh yeah. Like, this is now no longer, okay, this ramble is not on test or anything, but, and I am also not medical professional or medical scientist, so grain of salt for a lot of this, but I've been informed that a lot of modern machines installed inside of humans now have wireless features so that you can check up on it without having to cut the human open again,
Yes.
which probably just means it needs a bigger battery and it's always broadcasting a Wi-Fi signal. And like, if someone knew that person has this thing installed and got close to them with a transmitter and was able to break the encryption on the Wi-Fi, they could hack into their heart and up the speed of the pacemaker and give them a heart attack by pressing a button.
Don't mess with technology. It'll get you.
So I see what you're saying, and that is concerning,
Yes.
but I would rather have that as a slight risk than have to fillet open my patient every time I have to check the pacemaker.
Yes, I am in favor of being able to remotely check on the machine.
I would say
It
if
just
you're
needs
like
better
a,
encryption.
if you're like an FBI agent or a CIA agent and you needed a pacemaker, I would say don't use that one. But if you're anybody else, I think you would do it.
If you are anyone else, one should hope. Again, good idea, just needs a better firewall. Okay, I realize I didn't end up answering the question that was on the screen. So, all that said, let's compare the two most common light bulbs used in the United States, the new CFL bulbs and the old incandescent tungsten filament bulbs. Let's ignore the cost per light bulb first and just look at the energy used by each bulb. So the CFL bulb, the swirly type with the gas in it that you don't want to breathe if the tube cracks, uses 13 watts and can stay on for 6,000 hours on average before breaking. The old CFL bulbs have 60 watts and each one can only stay on for about 750 hours before breaking. So looking quickly at the kilowatt hours of energy each bulb will use during its natural lifespan, how does each bulb end up comparing?
78, like, do you want numbers right now?
Yes. Was that 78 kilowatt hours?
Yes, ma'am, sorry. The other one is 45.
Okay. So over their entire lifetimes, CFL will use this much energy, the old bulb will use this much energy. Does this by itself tell us which one will cost you less? No, because this bulb lasts a lot longer. How many times does 750 go into 600? Sorry, 6,000, thank you. 8. So one of these will ideally last you 8 of these. So 45 times 8 says that 8 of the old bulbs will spend that much energy. About somewhere between 3 and 4 times as much.
That's for every CFL.
Yes, there are some CFLs that use closer to 40 watts. I might have seen some that can even get as low as 30. But they don't last as long, and they still have higher wattage than the CFL bulbs. And additionally, I've done a lot of these types of questions and research because I did my research at BC with Dr. Odekor, who one of his research projects is into long-term energy efficiency of homes. So these sample questions come up a lot in this department, or similar things involving specifically light bulbs and refrigerators. And he goes really in detail into like the pricing of why you should be buying these. So if he ever starts talking about it, we'll go into that for a while. And even though a single CFL does cost more, $1.50 is less than 8 times 80 cents. So Dr. Odekor's lesson, at the very least, is buy CFL when you can. And similar, since if we assume 10 cents per kilowatt hour, that'd be $7.80 over however long this bulb lasts versus $36 just in electricity bills. This method can be used to estimate electrical costs for any machine, as long as you know its wattage and how long it is fully powered on. Fridge and AC are the biggest abusers, followed closely by your oven probably. It takes a lot of energy to heat up the entire inside of the oven and the stove top.
I think my desktop computer
Not as much as the oven probably. I can check real quick. I don't remember the specs from the PC that I built. Let's just go high-end, wattage of gaming PC. Most mid-range gaming PCs, let's just take an average, about 500 watts. How long would you run it each day?
Let's be optimistic and say 4 hours.
Yeah, okay, so 0.5 times 4 hours is significantly less than 1.2 times 24. So more than a light bulb, less than the big three of an AC refrigerator. Microwave's probably up there too, because it takes a lot of energy to
I
make
don't like
radio
a
waves.
garage door.
I wouldn't expect that to be a lot.
So would like a walk-in freezer at a restaurant be like a whole lot?
Sorry, say again?
Like a walk-in freezer at like a restaurant?
Oh, yes. That's probably their biggest energy cost. I need to ask my dad about that. He's been running kitchens for as long as I've been alive.
Sometimes when you work in a kitchen during the summer, you hide in the walk-in freezer. I did that a lot.
I was a bag boy at Kroger for exactly 1 year in high school, and that unfortunately overlapped with one of the hottest summers in Columbia. And after getting the carts in from outside, I would go hide in the walk-in freezer for like 5 minutes until someone found me. Garage door opener, average looks like about 600 watts, but it's only really on for like the 10 seconds it takes for the door to open and close. I suppose we'll be drawing a little bit of power at all times for the radio sensor, but not nearly as much as the actual motor.
Okay, I have one more question. What about a security system?
That would be on all the time. But there's no real moving parts, it's just sensors. It's 60 watts, so 0.06 times 24 is 1.44, significantly less than the full charge of a refrigerator.
So 14 cents a day?
Yes, not counting the fees for whatever you're paying the security company. Minor footnote about the energy cost though, because I didn't know this myself until this past year. These calculations are thrown off by something called peak hours, which is when the times per day the electric company decides we're going to hike the price up on you. Because in the
Have you ever been to Lake Jocassee, Crawford?
say that one more time.
Have you ever been to Lake Jocassee?
No.
It runs, like the Duke Energy power plant has dams up there, and during peak hours, you can see them moving water to like power, like when everybody gets home from work, like power all their stuff. And then they like, during the night, move it around again.
So yes, during the times per day when electrical draw for a region is at its peak, the companies just charge more because the demand is up and the machines are working harder. And what time that is depends on where you live and what season it is. And we just hit spring, so which hours that is just changed based on when everyone had on their heat versus when they now have on their AC. Usually it also peaks around dinner time when everyone's got the stove on. So those do mess up the calculations a little bit, but the baseline is still accurate. Because everything, like it increases by the same rate for all machines. It's not like one is suddenly good. Excuse me 1 second.
Turn off my refrigerator for 3 hours a day.
I mean, I turn off my Wi-Fi router when I'm not in this apartment.
I'm glad I don't know the language, because that'd be like micromanaging home language used to be doing.
It's hard for me, okay, so I have my own apartment. There's the house that my fiance and I are setting up, that we will move into after the wedding. And it's hard for me to not end up micromanaging the house's power as much as I do the apartments, because there's more people there. The Wi-Fi needs to stay on, as does the air conditioner. Okay, I've been kind of rambling all day about various parts about electrical power and bills. How do you guys feel, and any questions?
And so what were the final costs of the two bulbs?
Oh,
Did you just do it times what they're,
well, if we were looking at them for 6,000 hours, time it would take a CFL bulb to burn out, then just in electricity, the CFL bulb would be $7.80 plus the $1.50 to buy the CFL in the first place, so about $10 for 6,000 hours of use. The old light bulbs, just in running costs for 6,000 hours would be $36 plus 8 times the 80 cents to buy the light bulbs. So closer to $40.
Is there a fair deal for a year? You just like, do the number of hours a year, and then not how many light bulbs you're gonna be using a year?
I don't really know how many operating hours are in the average year for
Well,
one
I'm
light
just
bulb.
saying, the question asks, if we go 1 year, how much
Right.
else is there in each year?
I forgot to change the way that question was worded. I was going over the notes and meant to and then didn't. So I think the better baseline is, since this bulb lasts longer, what is the cost equivalently across that lifespan? It doesn't matter if that's a year or not. Excuse me. Any other questions?
How do like fluorescent bulbs compare?
Fluorescent is typically cheaper than incandescent,
Okay.
which is why most industrial settings and schools use these things. And that's why the CFL bulbs are that and downsized.
Okay.
The CFLs are the tubes, just the tubes are now helix so that they fit into the same shape as the old ones. So it's the same technology, you're just running current through a gas and the gas warms up. And like, we had the old filament bulbs because that's what was invented first, and that's all we had for a long time. And people just got used to using that in their homes and wanted the same shape for all the same lamps. Because no one really wanted to buy a house lamp that had one of those in it, or didn't really want these in their room.
So why is it that like these lights, you can hear them buzzing, but like with the CFL bulbs, you don't hear them buzzing?
I can sometimes, if it's very quiet and I'm constantly turning it on and off, I can hear occasionally. Odds are that a lot of work went into trying to silence them. Like the big chunky plastic thing at the bottom probably has something that may help with that. Good insight.
thank you.
Okay.
You're getting into it over there.
I can like sneeze in like 3s and 4s. Can't just
Same.
sneeze once.
I see that too.
Well, one sneeze is enough taking out.
See, I have multiple and one sneeze of mine is enough to start a typhoon. So, bad combo. Okay, I don't want it to take up too much time because kind of selfishly, I need to put a little more work into the lab before lab time starts. So we're probably going to end a little early for lecture today. I do want to at least begin talking about some magnet stuff because that's what the lab is about. That's what we're going to be getting into next. At the very least, official disclaimer. Electricity and magnetism are officially not the same thing. A bar magnet exerts a magnetic field, which is a distinct phenomena from the electric field an electron gives off. They are related, though. The 4 fundamental forces that literally hold the universe together are strong nuclear interaction, weak nuclear interaction, gravity, and the family of electromagnetic forces. And that family contains both electricity and magnetism. So they are not the same, they're just cousins. And because they're cousins, they get into fights at the family reunion. They affect each other, but not the same way they interact with themselves. Electric fields interact in a very predictable way. They either attract or they repel. Magnetic fields, similar to all the fields we've talked about so far, interact in a very predictable way. They either attract or repel. When you start mixing a magnetic field and an electric field is when things start to get weird. So, the official start of the notes that we will begin going over soon is magnets give off fields like gravity and like electric fields, but they are their own type of field, specifically magnetic fields. And to help determine the difference, Earth has a magnetic field. The Earth is a giant magnet. Earth does not have an electric field. The Earth is not a giant electron. Does that help? Or is that clear at least?
Yeah, that's definitely clear.
Okay, cool. So they do have fields though, and instead of going from positive to negative, the field lines point from north to south. So on a single bar magnet that has two different ends, the field looks something like this. Kind of an egg shape surrounding the entire magnet itself. And magnets are very useful. We use them to navigate by synchronizing them to Earth's magnetic field. And we can build magnetic trains out of them. We can reduce friction by using the magnets to kind of levitate things slightly so that they're not grinding into each other as much. And Earth's magnetic field is one of the reasons life is possible on this planet, because it's literally a force field protecting us from the dangers of space. More on that in a minute. Earth's magnetic field. Fun fact, Earth's magnetic field is not actually coming out of Earth's geographic north and south poles. If this is the north, if this is like the geographic Earth, magnetic Earth is like this. Very interesting. So if you follow a compass straight north, it won't actually lead you to the geographic North Pole. It'll lead you a couple dozen miles to the other axis of it. Actually, I think magnetic pole is somewhere drifting towards Alaska at this point. Fun fact, the magnetic poles move because, actually we're not entirely sure why, we think it has something to do with the magma in Earth's core. Since that's always moving, so is the poles of the Earth.
Oh, birds, I'm sorry,
They can navigate well enough to at least find Canada versus Jamaica.
Why where the magnetic lines are drawn over the map, are they so squiggly
Oh,
instead of just like this way?
I'm not entirely sure why
It's
it's
like the
matching.
20-degree east. It's not 45-degree turn.
That's degrees based on the round Earth, and that map of the states is flattened,
Okay.
so that's one part of it. That said, I'm not sure why they're squiggles as opposed to just arcs.
Yeah.
That I don't have a good reason for. It might have something to do with the magnetic elements in the Earth when these measurements were taken, because the rocks you're standing on would affect that.
So so like our north that we say is north, is it only north because we decided that? Like, did we decide that Antarctica is the top of the earth?
Yeah.
And why did that make
So-
more sense if it's the actual north magnet pole?
What we think of as Earth's north geographic pole is based entirely on the perspective of Europeans. Because when they started drawing their own maps, they put themselves on the top of the planet. Meanwhile, there are a bunch of maps drawn by native peoples in the southern hemisphere where everything's just upside down. And because Europe settled most of the planet, guess whose maps we use? Funny thing though, the pole that was arbitrarily labeled the North Pole is actually magnetic south. It's the south end of the Earth magnet.
Wonderful.
Very wonderful.
Thank you.
So we could technically just flip it and call Antarctica the top.
Yes.
That place.
Which side is the top of the planet is entirely just a matter of perspective.
So we could say like, the Bahamas is the top. Could we flip it that way?
You mean make the equator the north versus south pole? I mean, you could, but then it would be magnetic north and magnetic east and magnetic west.
Okay.
There we go, now we're talking.
Okay. I've been talking about the difference between electric and magnetism because magnetic interacts normally, linearly, in and out with magnetic. Electrical reacts normally in and out with electric. When you mix the two, things start to get kind of weird. Let's say, for example, that we have a magnetic field that points like this. This would be magnetic north, this would be magnetic south. The field lines are all pointing this way. And let's say that we drop in a proton that is currently moving up. So the proton is completely on its own volition, traveling in this direction as it passes through this magnetic field. What do you think would happen to it?
It would go towards whichever side has an opposite charge.
Okay. There is going to be a force acting on it. But magnetic north and south is not the same as electric plus and minus. So it's not actually going to swerve left or right. It's actually going to swerve. Let's see if I can get this right. Direction, magnetic field. The force that is going to act on this proton isn't going to pull it to the left, isn't going to pull it to the right. It's going to point that way, into the board.
Okay, now that's not how that should work.
It's 3D.
Why? Why does it do that?
Because magnets and electrics are weird cousins that get into fight at the reunion. They literally work perpendicularly to one another.
Okay.
And we don't need to do any math about it right now. I just want to introduce you to this fact to get you used to the weirdness that is magnets.
So
Keeping in
magnetic
mind-
forces and electrical forces work perpendicular to each other. So if one is in the X and Y plane, the other one is in the Z plane.
Well,
Going in and out versus laterally.
there's a rule that is common to use to figure out the direction that everything is going to point in. And yes, it involves using your right hand.
Again, the
Physicists.
thing already hurt my brain.
So if the proton is moving in the direction that your fingers point, and the magnetic field is coming out of your hand, kind of like you're blasting it, then the force the field will exert on the proton is going to point in the direction of your thumb.
I decided that physicists are words.
Thank you. And we call it the right hand rule because it doesn't work if you use your left hand. So, key takeaways here, magnets are weird, and this is the reason why Earth's magnetic field protects it from space dust and space radiation, and why all of our electric generators work. One of the things I'm going to hopefully try to show you in lab by physically building similar machines is that magnetic fields do make charges move, just in weird directions. So if you have a magnetic field that is constantly changing direction, you can create an electric current by forcing the proton to move in a specific direction, or the electron. So we commonly have machines that use magnets to make electricity. Additionally, think of this field as Earth's magnetic field. Think of this proton as space debris. If this was heading towards Earth, suddenly it's being redirected that way.
Is there anything it's gonna redirect like towards us?
If something is coming, hang on, something's coming from space into the magnetic field, it would ping down away from the planet.
So it depends on how fast the wind.
Wait, hang on.
Right?
The field would go from the South Pole up, so it would ping that way away from the planet.
Why wouldn't you, like, why are you not supposed to touch a magnet to like your phone or your computer?
Because the magnet inside will mess with all the electrons moving inside of it and maybe cause a few logic gates to open that aren't supposed to, and since the storage, the memory of a phone is entirely stored logic gates, it can wipe the memory, is the main problem. When I was a kid, and my dad loaned me his big old CRT TV to play video games on, I once accidentally put magnets on the top of it, which surprisingly didn't ruin it. It just changed the colors of the upper left pixels. So my health bar in Transformers was no longer purple, it was yellow. But I didn't know that until I removed the magnet and it changed in front of me.
Can you explain what we're doing in lab again?
In lab, I'm going to show you a couple of scenarios where magnetic fields can affect electrical processes and vice versa. And the first two parts will be about building a couple small circuits that show these things physically in ways you can build them yourself. Then there will be some simulator questions that actually show the field lines and interactions.
So we'll do that on our computers, you mean?
Yeah. You can work on that in the lab room if you want. You can also go on your own and turn it in at the end of the week.
But we would have to start it in Thursday, right?
I'll take them Friday.
Oh, okay.
Wait, we don't meet Friday.
Yeah, that's
I'll take them next Tuesday.
Thank you.
Okay, I admit it's been kind of a rambly lecture, and magnets are weird. Any questions? Any questions? Otherwise, we can break for today while I scramble to get lab ready.
While you get lab, how long do you think it'll take you to get lab ready?
My timeline is to be ready by the start of the normal start time for lab.
Oh, okay. I was gonna go on a walk. It's gonna take you a while.
Well, I'm planning on, I need to get it physically set up and I need to get the sheets printed off, but I'm planning on it not taking a supremely long amount of time because I have to actually go get my COVID vaccine at 3:30.
Yeah.
Wait, you got 23 minutes. Let's do that.
I have all this on, right? Because if I don't, like, I'll just,
Okay.
I know myself, and I have to leave. I did that last week and it's screwed up.
Yes. And even if you weren't, the simulator.
Kids are more practice.
So, just reserve, talk to you, Robert,
And then
He's saying,
He said what?
he doesn't